Location decisions are always difficult. Managers have to consider many different factors and there are serious consequences for making mistakes. Some of the factors in location decisions can be measured or at least estimated, such as operating costs, wage rates, taxes, currency exchange rates, economic growth, distances from customers and suppliers, development grants, and so on. Other factors are non-quantifiable, such as business strategies, quality of infrastructure, political stability, social attitudes, industrial relations, legal systems, cultural lifestyles, and so on. To include all of these factors, managers need a hierarchy of decisions. At the top of these are broad decisions about the geographic regions to work in. Then come more local decisions about countries or areas within this region. Then they look more closely at alternative cities and towns within this area. Finally, they consider different sites within a preferred town. We can include this hierarchy in a general approach that coordinates location decisions with other decisions about the supply chain, particularly fitting it into the logistics strategy. Review the aims of a supply chain. A logistics strategy and other plans specify the goals to be achieved by location decisions. This gives the context and requirements of any location. Do a logistics audit to describe the current logistics system, including the location of facilities, connecting networks, measures of performance, and industry benchmarks. This shows how well the current supply chain is achieving its requirements. Identify mismatches between goals from step 1 and actual performance from step 2. Examine alternatives for overcoming the mismatch, looking to see how and where the structure of the supply chain can be improved. This step considers the effects of alternative supply chain configurations, including general locations for facilities. This might identify the best areas for locations. Make location decisions. Having considered the general features of a supply chain in step 4, the step considers alternative sites that are available and chooses the best. This adds most detail, moving from areas down to choosing a specific site. Confirm the location, making sure that the location identified in the previous step really is best, and adding details of the facilities to be built or changed, capacities, resources available, and so on. Implement and monitor the solutions, doing whatever is needed to execute the changes and continuing to check performance. This procedure emphasizes that the hierarchy of location decisions must fit into the broader logistics and supply chain strategy. If the supply chain strategy calls for short delivery times, then facilities must be in locations that can achieve these. If the strategy calls for low costs, facilities will probably be centralized to get economies of scale. The main decisions about locations are made in step 4 and 5, and these set the overall shape of the supply chain, which should be designed to achieve the broader organizational aims. In particular, step 4 gives decisions in principle along the lines of "we need a warehouse in the Benelux countries," for example. Then the step 5 considers the sites that are actually available and identifies the best. Step 6 adds commercial and other details needed to finalize the choice of site. Unfortunately, this procedure is rarely as easy as it seems, and it usually needs a lot of iteration through the steps before it gives a satisfactory solution. We mentioned the location of suppliers and customers and the operating costs, but many factors might make one region more attractive than another. Traditional economic theory takes a rather passive view and says that a region's attractiveness comes from the inherent features of land, labor, location, local population size, and natural resources. This has been refined to more positive views such as Porter's, describing the attractiveness in terms of factor conditions, key factors that encourage production, demand conditions related to customers in local economy, supporting industries, typically commercial services, and company strategy, structure, and competition, the general state of competitiveness. In practice, the attractiveness of a region is judged by more specific features, with the following list including the most common. Managers should consider these and all other relevant factors before making a strategic decision to use locations in a particular region. Location of customers and markets. Service providers often need personal contact with their customers, so they have to be physically close, which is why you find shops, buses, libraries, restaurants, solicitors, and banks in the center of towns. Similar arguments hold for manufactured goods that have a low value density, which is why you also find local bakers, brewers, dairies, and egg producers. Being close to the customers allows firms to reduce delivery costs and give high level of service. Location of suppliers and materials. Manufacturers are more likely to locate near to supplies or raw materials, particularly if these are heavy or bulky. This is why power stations are close to coal mines, steel works are close to iron ore, and pulp mills are near to timber forests. Some operations have to be close to perishable materials, which is why fruit and vegetable processors are close to farms and frozen seafood companies are near fishing ports. Location of competitors. This can make a location less attractive when competitors offer similar products and are aggressively fighting for a larger share of a fixed market. This means that you rarely find two hospitals next door to each other. On the other hand, it can make a location more attractive when a cluster of similar organizations attract new customers and consolidate expertise. You often see the results when a cluster of banks open in a commercial center or nightclubs open in the same street. Infrastructure and availability of transport. It is essential to have appropriate transport to move materials. Often this means access to a good road network, but it might also mean links to rail, air, sea, or pipelines, or intermodal terminals. Culture. It is easier to expand into an area that has a similar language, culture, laws, and costs than to expand into a completely foreign area. Government attitudes. National and local government policies can seriously affect attractiveness. Some governments do not welcome foreign investment, usually because they want to control foreign influences, and investment for instance, in some countries, fell when a less welcoming government came to power, but most governments give incentives to attract companies to an area. Direct costs. These are the costs of operations, including wages, materials, overheads, utilities, transport, interest rates, and so on. Clearly, the most attractive locations offer a combination of low direct costs and high performance. Unfortunately, lower costs often mean lower productivity, so managers look for a balance, which might encourage them to accept high cost as a means of getting related benefits. Indirect costs. These include local taxes, currency exchange rate variations, restrictions on exporting funds, inflation, and charges on the payroll, such as social insurance, pension, and social costs. This can also appear as controls on local operations and ownership, typically insisting that a local company has a controlling interest in a joint venture. Social attitudes. Some countries put more emphasis on social welfare than others, and they might have higher union membership, protective legislation, and emphasis on individual rather than corporate benefits. Quality of life. It is difficult to measure or even describe a region's quality of life, but it essentially shows how much people like living there. This typically depends on a range of factors like climate, housing, healthcare, education, cost of living, crime, environment, public transport, and so on. An attractive quality of life means that it is easier to recruit and retain employees as well as suppliers and customers. Local control. We know that there are differences between international, multinational, and global operations. If you go into a McDonald's restaurant anywhere in the world, you will see virtually identical operations. It is easier to control operations in this way, but it loses the benefit of local knowledge and practices. Other organizations blend into the local environment and adapt their operations so they are more familiar to their host countries. And lastly, organizational strategy. Apart from all rational factors, an organization, or more realistically its senior managers, might simply prefer some locations to others. After making a decision about the geographical region, an organization has to look in more details at areas and then individual sites. There are many analyses to help with this decision, usually based on some kind of investigation of costs. One approach that is not recommended is personal preference. Managers often seem to be subjective and choose sites they like, perhaps in the town where they live or grew up in, or where they spend their holidays. These decisions may be successful, but they are unreliable and often lead to very poor choices. Because you like spending your holidays in a particular town, it does not mean that this is the best location for a business. There are two distinct approaches to location decisions. The first, infinite set approach, which uses geometric arguments to find the best location, assuming that there are no restrictions on site availability. And second, feasible set approach, where there are only a small number of feasible sites that managers have to compare and choose the best. An infinite set approach finds the best location in principle, and then managers can look for an available site nearby. A feasible set approach compares sites that are currently available and chooses the best. These approaches are often used together with an infinite set approach homing in on the best area to locate, in principle, and then a feasible set approach comparing available sites nearby. Let's explore the infinite set approaches. Many different approaches can look for the best location in principle, and we can illustrate their general approach by finding the center of gravity of demand. Managers can locate a facility near to customers, or they can locate it near to suppliers, or they can compromise and put it somewhere in between. A location near to customers gives fast customer service and low cost for transport out to customers, but long journeys in from suppliers. Conversely, a location near to suppliers moves products quickly into the supply chain and gives low costs for inward transport, but now there are long journeys out to customers. If we add the two transport costs together, we typically get the graph shown here. This suggests that a compromised location somewhere between customers and suppliers balances the costs and gives the lowest total. A way of finding this compromised location calculates the center of gravity of supply and demand. This looks at the map coordinates x and y of each customer and supplier and finds the weighted average of them. In particular, it calculates the center of gravity x0 and y0 from these formulas. We can illustrate this calculation by a small and simple example. ABC Company is building a central logistics center to collect components from 3 suppliers and send finished goods to 6 regional warehouses. The map coordinates for them and the weights to be moved are shown in the table here. Where is the center of gravity of demand? The figure shows a spreadsheet with the location of customers and suppliers along with the calculation for the center of gravity. You can see that columns E and F calculate Xi and Wi and Yi and Wi, respectively, with the sums given in cells E18 and F18. Dividing each of these by the total weight given in cell D18 gives the following calculations, which confirms the result given in the spreadsheet. A good place to start looking for a location is around 45.5 and 50.3. As this is very close to Warehouse 6, it is probably better to expand on this site rather than look for an entirely new location. The center of gravity often gives a reasonable location, but you have to be a bit careful. We can easily show this by considering a location decision in Alberta, Canada. Suppose that you want a warehouse to deliver 20 tons of materials a day to Edmonton and 40 tons a day to Calgary. These two cities are connected by a straight road 300 kilometers long. If the costs of getting deliveries from suppliers are the same regardless of location, where would you build a warehouse? Taking the coordinates of Edmonton as 0, 0 and those of Calgary as 300 and 0, the center of gravity is 200 and 0, or 200 kilometers from Edmonton. A warehouse here would have to move 200 multiplied by 20, or 4,000 ton-kilometers to Edmonton, and 4,000 ton-kilometers to Edmonton, giving a total of 8,000 ton-kilometers. But if you build a warehouse in Calgary, you would only have to move 20 multiplied by 300, or 6,000 ton-kilometers to Edmonton. This suggests a rule of thumb which says that a good location is in the center of highest demand. We can improve the basic center of gravity model in many ways, such as using actual road distances rather than map coordinates for the calculation. Often the speed of delivery is more important than the distance, so we can replace distance by travel time, or we can use some more direct measure of cost. Beyond this, we have to use a more sophisticated optimizing models, usually based on linear programming. These look for a theoretical optimal solution, but they are much more complicated. The extra effort may not be worthwhile, as more complex models do not guarantee better results, and the answers are still based on a series of approximations and assumptions. Regardless of how sophisticated the model, all infinite set approaches have the weakness that their suggested locations may not be practical. For instance, there may be no suitable site available anywhere near the solution, or available sites may be too expensive, or further development may be prohibited, or there may be no roads or workforce. Or the solution might be at the top of a mountain or in the sea. Feasible set approaches consider a small number of sites that actually are available, compare them, and identify the best. An obvious analysis for this calculates the total cost of working from each location. In practice, the cost of running a facility may be largely fixed regardless of its location, and then instead of looking at all those costs, we can concentrate on the variable ones. Then we might find that the total variable cost of using a location equals to variable operating cost, inward and outward transport cost. Unfortunately, even this is difficult, as we have already said that managers cannot know the real cost before they actually open a facility. For example, how can they know the cost of outward transport when they do not know exactly who their customers will be, where they are located, or how much they will buy? Even with good forecasts, demands and costs change over time, and the analysis soon become outdated. On the other hand, the strength of cost calculations is that they are useful for comparisons, even when they do not necessarily show the real costs that will be incurred. If the analysis shows that one location costs $5,000 a week, while another costs $10,000 a week, this gives a useful comparison, even if the figures are only surrogate measures rather than accurate forecasts. Let's see an example. ABC Company wants to build a depot to serve 7 major customers at the following coordinates, shown here. Average weekly demands in vehicle loads are 20, 5, 9, 12, 24, 11, and 8 respectively. There are three alternative locations available at the following coordinates: 120, 90, 160, 70, and 180, 130. Which is the best site if operating and inward transport costs are the same for each location? We only have a limited amount of information for comparisons, so we as well make the calculations as easy as possible. For a start, we can assume that operating costs and inward transport costs are about the same for each location, so we do not need to consider them. We do not know the exact cost of delivering to each customer, but we can assume that the transport cost is proportional to the distance moved. In fact, we can use another shortcut here and assume that the transport cost is proportional to the rectilinear distance between points, where this is defined as difference in x coordinates plus the difference in y coordinates. Then, using the information here, we can calculate the rectilinear distance from site A to customer 1, and that is 40. Now, rather than using cost, we can compare locations using the surrogate measure of total load multiplied by a rectilinear distance moved. This figure shows all those calculations for all sites and all customers, multiplying the total load by the rectilinear distance, and we see that the best location gives lowest values. Site C is clearly the best option. We can use a variation of costing models to consider a related question which asks how many facilities to use. The principle here is that each additional facility gives a smaller benefit. There is some optimal number of facilities beyond which the extra costs are greater than the likely benefits. We can find this optimal number using the following argument. When an organization concentrates activities in a few key locations, such as main logistics centers, inward transport consists of a few large deliveries and the cost is low. However, the facilities are on average further away from customers and the outward transport costs are high. This option generally gives lower customer service and is used when cost is a major consideration. When there is a large number of facilities, such as retail shops, inward transportation costs of small deliveries to more destinations and the cost is high. However, facilities are on average nearer to customers, so they have the benefits of higher customer service and lower outward transport costs. Operating costs also vary with facility size, with larger facilities generally more efficient and giving economies of scale. But remember that larger facilities do not necessarily give economies of scale, and there can be real diseconomies caused by higher cost of supervision, coordination, communication, and so on. If we plot these transport and operating costs against the number of facilities, we typically get the pattern shown in this figure. Adding the three costs gives a U-shaped curve with a minimum that corresponds to the optimal number of facilities. This suggests the best number of facilities, but managers have to consider a whole range of other factors before making such an important decision, such as management overheads, communications, fixed costs, employment effects, customer service, and so on. Costing models can give useful comparisons, but they have weaknesses, including the difficulty of finding accurate costs, data that depends on accounting conventions, costs that vary over time, customer locations not being known in advance, order sizes not known in advance, factors that cannot be costed, and so on. Because of this, it is often better to use some other measures for comparison. The most common alternative is a scoring model. Scoring models focus on the different factors that are important for locations, but which cannot easily be costed or quantified. We have already seen the type of factors that is important in selecting a region to work in and can develop similar lists for the more detailed decisions. A more detailed list of factors include In the country and area, availability, skills, and productivity of the workforce. Local and national government policies, regulations and attitudes. Political stability, economic strength and trends. Climate and attractiveness of locations. Quality of life, including health, education, welfare, and culture. Location of major suppliers and markets. Infrastructure, particularly transport and communications. Culture and attitudes of people. In the city or town, population and population trends. Availability of sites and development issues. Number, size, and location of competitors. Local regulations and restrictions on operations. Community and local services, including transport and utilities. In the site, amount and type of passing traffic, ease of access and parking, access to public transport, organizations working nearby, total cost of the site, and potential for expansion or changes. Although we cannot quantify these factors directly, we can move in this direction by awarding each a score. You see this approach with hotels where it is difficult to measure their quality, but the best are awarded 5 stars and lower quality ones have fewer stars. This idea of assigning subjective scores is the basis of scoring models. These need the following 5 steps. Decide the most important factors for location decisions. Step 2. Give each factor a maximum possible score that shows its importance. Step 3. Consider each location in turn and give it an actual score for each factor up to the maximum. Step 4. Add the total score for each location and find the highest. And last, step 5. Discuss the results and make a final decision. Now let's explore an example. ABC Company considered 4 possible locations for a new distribution warehouse. After many discussions, they compiled a list of important factors, their maximum scores, and actual scores for each site. Which site would you recommend? The most important factors are those with highest maximum scores, which are the infrastructure and closeness to customers with 20 points each. The closeness of suppliers is a bit less important with up to 15 points. And then come climate, accessibility, and community attitude. Adding the scores for each location gives the following result. This score suggests that location C is the best. The company should now consider all other relevant information before coming to a final decision. We had just listed some factors that might be included in such models, but the details of these and their relative importance depends on the circumstances. Combining the two approaches. We have outlined several models for location, but these are by no means the only ones, and a huge amount of work has been done in this area. Useful models range from simple rules of thumb through to complex optimization methods. But these methods need not work in isolation, and they can be combined to give more thorough views. For instance, we could use an infinite set approach to find the best general area, followed by a finite set approach to compare available sites in the area. Sometimes it is difficult to relate the models we have described so far to actual road layout and geographical features. But another type of model specifically considers the road layout. There is a huge variety of models, but we can illustrate their approach by 2 standard ones, known as the single median problem and the covering problem. Let's start with the single median problem. Imagine a cluster of towns connected by a network of roads. There are demands for some product in each town, and you want to locate a depot to deliver to these towns. An interesting result here is that the best location is always in one of the towns, so we only have to compare locations in each town and identify the best. Suppose that you want to find the location with the shortest average travel distance to all customers. This is called the single median problem. To find the single median, you form a matrix of the shortest distances between each pair of towns. Now the average of each column in the matrix shows the average distance from one town to the others. So the column with the lowest average identifies the single median. Let's see an example. ABC Company delivers goods to 8 towns with locations and distances shown below. Which location minimizes the average delivery distance? We start by building a matrix to show the distances between each pair of towns shown here. That shows that DI is an average 11.3 from the other towns, and as this is the lowest, DI is the single median. When there are different amounts to be delivered at each town, we should weight the distances by the amount moved. If the figures by each town in the figure here show the amount to be delivered, how does that affect the single median? Instead of finding the average distance in each column, we have to multiply this by the weight shown in column B here. Taking one column, for example C, this shows the distance from AL to each other town, and multiplying this by corresponding weight in column B gives the weight distance between AL and each other town. Adding these down, the column gives the total weight distance for a logistics center in AL shown in row 12. Dividing this by the number of deliveries, 8, gives the average weight distance. Repeating this calculation for each of the other town gives the results in row 13, with EN now the lowest. Now let's continue with the covering problem. Sometimes the average distance or time to a facility is less important than the maximum. Classic examples of this are fire engines and ambulances, which try to respond to emergencies within a maximum time. In the same way, suppliers might guarantee deliveries within a specified period. This is the basis of the covering problem. There are two versions of the covering problem. In the first version, an organization wants the single location that gives the best service to all towns. In other words, it wants the lowest value for the maximum time needed to reach any town. A company might find that a warehouse in Vienna could reach any of its customers within 12 hours, while a warehouse in Prague could reach any customer within 10 hours. Then Prague is clearly better. To solve this type of problem, we simply compare the longest journey times from each location and choose the location with the shortest. The second version of the covering problem specifies a level of service that must be achieved, such as delivery guaranteed within 5 hours. The problem is then to find the number of facilities needed to achieve this. As with all such problems, we do not need to worry about the calculations, as a lot of software does this automatically. Let's now explore an example. The figure below shows part of a road network with the travel time in minutes on each link. Where would you locate a depot to give best customer service? How many depots would be needed to give a maximum journey of 15 minutes? This figure here on the left shows the results from a simple spreadsheet add-on that solves lots of types of routing problems. This finds the best single location as C, which has a maximum journey of 25 minutes. If this is too much, facilities at A and I will reduce the maximum journey to 15 minutes.